Hi, and welcome to this lesson on the elements of a radio link. The purpose of a radio communications link is to move information from one point to another using radio waves. So, a radio link will consist of a transmitter, a radio wave, and a receiver. Now, obviously there's much more to consider, and so in this lesson I'm going to spell out the next lower level of detail. And that's really all I'm going to do in this lesson. The details of each element of a radio link will be discussed in future lessons. In order to have something concrete to discuss, we'll consider a specific kind of radio known as a single conversion superheterodyne. This type of radio is probably the simplest type of radio that contains all the elements that are commonly seen in modern radios generally. We'll also say something about how the radio wave aspect of a link plays a role in radio link architecture, and this is through propagation loss, interference, and noise. Finally, we'll talk about a simplified architecture for receivers and transmitters, just to drive home the point that there are many ways that radios can be implemented. In this lesson, I want to walk you through a complete radio link, beginning with information coming in at the upper left of the slide, the radio wave along the right side of the slide, and the information exiting at the bottom left of the slide. Now, this will be an example, and what I'm about to explain will certainly not be the only way this can happen. However, what I will show you is very common, and really most other possibilities are variations on this theme. Let's begin with the transmitter. The transmitter must accept information and somehow generate a radio frequency signal representing that information. The first step is modulation. Modulation is converting the information in whatever form, analog voice, data bits, whatever, into some other form that is suitable for transmission as a radio wave. Possible modulation schemes include amplitude modulation, frequency modulation, binary phase shift keying, quadrature amplitude modulation. The list goes on and on. These schemes are explained in another lesson. The key idea here is that we are converting information in its native form into a particular waveform that is suitable for transmission as a radio wave. These days it is very, very common to do modulation within digital hardware, perhaps within a computer of some kind. If this is the case, then the output of the modulator will be quantized samples of the waveform that we want. For example, perhaps the output of the modulator is a 12-bit value which is updated once per microsecond. So we'll need to convert that into a proper analog waveform. The thing that does this is a digital to analog converter. This device is indicated as D/A in this diagram and might also be referred to as a DAC or DAC. Now here's the thing you need to know about digital to analog converters. It's usually not practical to use them to produce output at the frequency that you intend to transmit at. One problem is that the power consumed and dissipated by a D to A is large, and that increases with increasing frequency. Another problem is that, all things being equal, D to A's work better at lower frequencies than at higher frequencies. So it's usually desirable, or necessary, to use the D to A to output a signal which is at a lower frequency than you plan to transmit, and then to shift the output of the D to A upward in frequency as a separate step. This shifting of frequency is called upconversion. The simplest form of upconversion is shown here. Here we're using an oscillator to generate a sinusoidal signal, and you would literally multiply that signal with the output of the D to A. That gives you a signal centered at the sum of the center frequency of the output of the D to A and the oscillator frequency, and then that's the frequency that you would transmit. This feature is what makes this architecture single conversion superheterodyne. Now, obviously I'm leaving out a lot of detail, but let's keep this simple for now, and we'll return to the topic of frequency conversion in another lesson. The output of the upconverter is now at the frequency we want to transmit, but typically it will be too weak. So the final step before applying the signal to an antenna is to amplify the signal. The amplifier used in this particular application is known as a power amplifier, or simply PA. The PA is always the last amplifier before the antenna. From a spectrum management perspective, it's also useful to know that imperfections in the PA can, and do, result in unintended spectral content. For example, PA designers and spectrum managers both worry about spectral regrowth. This refers to the tendency of the PA to spread power beyond the desired bandwidth of the signal. And with that, a radio wave is launched by the antenna and propagates away from the transmitter. Some part of that irradiation arrives at and is captured by the antenna of the receiver. On the way to the receiver's antenna, two important things happen. The first thing that happens is that there is loss. Loss is unavoidable because the radio signal spreads out in many directions, so what arrives at the receive antenna can never be more than a tiny fraction of what was transmit. This loss is often more than, or much more than, 100 dB. 100 dB is 0.0000001% of the transmitted power. The second thing that happens is that the receive antenna captures other signals, including interference from other transmitters, and also noise from the myriad things that can generate noise at radio frequencies. So we can see right away that the receiver will need to overcome at least three problems. First, the receiver will need to apply a lot of gain in order to make up for the power that was lost in propagation. Second, this gain needs to happen without introducing too much additional noise. And third, the receiver will need to be robust to the presence of interference. The solution to the first two problems, that is gain and low noise, is called a low noise amplifier, or LNA. The purpose of an LNA is to amplify the signal without simultaneously introducing too much noise. Because we are explicitly worried about noise in this particular stage of the receiver, we've identified this particular internal noise explicitly in this diagram as the red arrow labeled internal noise. This arrow appears here because, in a well-designed receiver, the noise from other components of the receiver really shouldn't matter. That LNA should have increased the incoming signal level by enough that the noise in subsequent components of the receiver is small relative to the noise at the output of the LNA. Before moving on, let me be clear that there will normally be additional amplifiers distributed throughout the receiver. I call out the LNA here explicitly because of the outsized role that the LNA plays in determining the sensitivity of the receiver, and often in determining other key performance aspects of the receiver. And here's the rest of the receiver. In this example, each subsequent stage of processing performs more or less the opposite function performed by the analogous stages in the transmitter, namely, down conversion to undo up conversion, analog to digital conversion to facilitate demodulation using digital hardware, and then demodulation to recover the information from the modulated waveform. However, there are a few things that we need to say about each one of these functions. First, why down conversion? Well, typically we prefer to do demodulation in the digital domain, which means we need to digitize the signal first. That's why we need the A to D. But A to Ds, like D to As, dissipate a lot of power and have better performance at lower frequencies, so we downconvert first. Like up conversion, we can do down conversion using an oscillator as shown in the diagram. And all this makes this scheme single conversion superheterodyne architecture, just as in the transmitter. One more thing to note here. Note that the down converter includes filtering. Filtering is required because the receiver receives not just the desired signal, but also the undesired signals, namely the interference. If there is no filtering, these additional signals can easily degrade the performance of the receiver. And there are many ways that this can happen. But one common way for this to happen is for the undesired signals, which are nearby in frequency, but also very strong, to overwhelm the receiver. Now, once again, I want to emphasize that what I'm showing here is only one of many possible architectures. Single conversion superheterodyne architecture means that the modulation processing and the RF processing happen at different frequencies. and the conversion between frequencies is accomplished by mixing the associated signal with the signal from an oscillator. Other possible architectures include tuned RF, multiple conversion superheterodyne, direct conversion, direct sampling. I'm not going to discuss these here, but you should know that these exist, and each of these will have different advantages and disadvantages. Not only is single conversion superheterodyne not the only possible architecture, but also there are multiple ways to do even single conversion superhet architecture. A common alternative scheme for a radio link is the simpler architecture shown here. You can immediately see this is much simpler because there's no digital processing. Everything is done in the analog domain. In the transmitter, the information is used directly to vary the magnitude and/or frequency of an oscillator, which is directly generating the signal at the RF frequency without the need for upconversion. For example, we could use this scheme to generate amplitude modulation, or on-off keying, by manipulating the magnitude. Or we could use a scheme to implement frequency modulation by having the input signal manipulate the frequency. Now on the receive side, we have once again single conversion superhet architecture, but in this case it's not quite the same as before. Here the demodulation is done in the analog domain with no need for digitization. Just a few decades ago, this type of architecture was really the only practical way to do radio. Suitable digital processing and D to A's and A to D's were not available for this application. Now that they are, we have options, and we're not limited to all analog architecture, such as what is shown here. However, this architecture remains important for several reasons. For example, at very, very high frequencies, the high end of the millimeter wave band, for example, or for very, very high powers, when you're talking about, say, megawatts of transmit power, this transmitter architecture often turns out to be the way to go. This architecture also shows up in applications where cost, power consumption, and complexity must all be very low. Of course, what you lose in that case is flexibility. Really, it's quite difficult to implement modern digital modulations in an architecture like this. So, time to summarize the main points of the lesson. We talked about single conversion superhet architecture and the fact that this is common, but not the only way to go. Once again, other possibilities include tuned RF, a multiple conversion superhet, direct conversion, direct sampling, and so on, and perhaps those will be addressed in future lessons. But if you have a good understanding of single conversion superhet architecture, then you understand most of the important elements in radio link design generally. We talked about transmitters and the fact that they must be designed to control undesired spectral content, a principal issue being the spectral regrowth of power amplifiers. Receivers must be designed to account for high propagation loss, external noise, and interference, and much of this burden falls on the low noise amplifier and the filtering that's done in down conversion. Finally, details on all of these things, frequency conversion, filtering, and so on, are topics for later lessons. That concludes this lesson on the elements of a radio link. Thanks for listening.